Dear colleagues, in the past sessions, we have all enjoyed the excellent presentations of Graham, Zeishan, Patrick, Christophe about the future of thermodynamic temperature, the international temperature scale. So I thought that for this last session, I could offer a reflection on the historical development of the concept of temperature and its measurement scales. So in the first part of my presentation, I will recall the main milestones in the path to our current understanding of the thermodynamic temperature and its measurement scale. And while doing that, I will introduce the basic concepts of measurement theory, which, as you will see, offers interesting insight into the definition of temperature and its measurement scales. In the second part, I will summarize the evolution of the thermodynamic temperature scale over the past 100 years. And then I will conclude my talk with some final remarks about what has changed since the last redefinition of the Kelvin of 2019. So I searched for the definition of thermodynamic temperature in the BIPM website, but I could not find it. The BIPM website deals with the SI unit of thermodynamic temperature. It describes how the SI unit is defined. We all know by taking the fixed numerical value of the Boltzmann constant to be equal to this number. Just a moment, I start the pointer. Yes. And the BIPM website describes also how the SI unit is realized through the Mise-en-pratique. But how is thermodynamic temperature defined? There are many approaches to define temperature. The approach we are probably all most familiar with is the so-called phenomenological approach, which is based on the principles of classical thermodynamics. And there is also the axiomatic approach, which is based on a mathematical theorem on differential forms, which was demonstrated in 1909 by a Greek mathematician, Karateodory. This theorem captures the essence of the second principles of thermodynamics, and it demonstrates, taking the second principle as an axiom, the existence of temperature as an integrating factor for the differential of heat, dq. So temperature exists as a kind of magical function of the thermodynamic parameters that when you put it at the denominator of the differential of the heat, it magically transforms it into an exact differential, which then we know is the differential of entropy. And of course, we are all reassured by this theorem because if temperature exists, then it means that we are not all wasting our time in trying to measure something that doesn't exist. Well, there are also microscopic approaches. There is kinetic theory of gases, statistical mechanics, and quantum mechanics. Statistical mechanics is, in a way, the approach which is implied by the new definition of the Kelvin of 2019. So I will tell you now the major milestones that led to the modern definition of thermodynamic temperature. The first ingredients were thermal equilibrium and the zero principle. Well, thermal equilibrium, you all know what it is. The zero principle is basically the transitive property of thermal equilibrium. So if A is in thermal equilibrium with C and B is in thermal equilibrium with C, then A and B are in thermal equilibrium with each other. And these two ingredients allow to have a procedure to determine equality of temperatures. So given any two systems, you can determine whether they have the same temperature or not by bringing them in mutual thermal contact and by looking at what happens. According to measurement theory, when you can determine equality, you can already create a first simple type of measurement scale. It is called nominal scale, and one typical example of nominal scale is the numbers on the uniforms of football players. In this case, the numbers are used as names, and the actual number has no meaning. So you cannot say, for example, that player number 10 is 2 times better than player number 5. The next ingredient is the second principle of thermodynamics, and the second principle provides a procedure to order temperatures because heat spontaneously flows always in the same direction from the higher temperature to the lower temperature. Then we can label each temperature with a serial number, but still we cannot assign a numerical value to it. We have, a mathematician would say, a so-called hotness series, a series of members which are ordered. Again, according to measurement theory, we can create a second, more interesting type of measurement scale. It is called ordinal scale because we can establish equality and order. So not only you can say whether two quantities are equal or not, but you can also say which one of the two is higher. Next, empirical temperature scales came. An empirical temperature scale is any order-preserving correspondence of the hotness series. So an empirical temperature scale, it simply assigns a number to the hotness series at the condition of maintaining the order. The problem with empirical temperature scales is that there is not only one. Actually, if T is an empirical temperature scale, then any monotonic function f of t is also an empirical temperature scale. And that's the reason why historically we had a proliferation of empirical temperature scales. According to measurement theory, empirical temperature scales are ordinal scales. So the historic Fahrenheit and Celsius mercury-based scales are ordinal scales. Calendar scale is an ordinal scale. And in principle, all the international temperature scales are ordinal scales. There is a problem with ordinal scales. They do not preserve equal intervals. And I will show this with a simple example on the Celsius mercury-based centigrade scale. If you look at how the Celsius mercury-based centigrade scale is constructed, you have a mercury in glass thermometer, as you can see here on the right, and then you put a mark corresponding to the ice point, you put a mark corresponding to the steam point, and then you divide the interval between the two marks in 100 equal intervals. So this is a perfectly defined ordinal scale because it preserves equality and order, but it does not preserve equal intervals. So if you take an interval close to the ice point, for example, P1, Q, and you take an identical interval close to the steam point, R, P2, then numerically they are equal, but they do not correspond to equal differences in hotness because mercury does not expand linearly on temperature. So we needed a couple of more ingredients to arrive to the modern definition of thermodynamic temperature. And one of these ingredients was the Carnot theorem. The Carnot theorem states that all Carnot engines that operate between two thermostats at temperature T1 and T2 have the same efficiency. And from this, it follows that the ratio of the heats exchanged by the two thermostats is equal to the ratio of the same universal function of T at T1 and T2, as you can see here in this equation. Well, moving from Carnot theory, Thomson made a first proposal in 1848, which is not the final proposal on absolute temperature, which is the modern definition of thermodynamic temperature. Thomson conceived a cascade of Carnot engines, each one producing the same mechanical work, as you can see here in this diagram on the left. And such a cascade would operate between thermostats separated by the same temperature interval. In this way, each degree of temperature produces the same amount of mechanical work at any temperature. And this scale would preserve equal intervals of hotness. So this scale would solve the problem that I've showed you before with the ordinal scales. Again, according to measurement theory, this Thomson first proposal for absolute temperature belongs to a third type of measurement scale. It is the interval scale, and the interval scale can establish equality, order, equal intervals, and it has an arbitrary zero. Then in 1854, the final proposal of Thomson came, and he simply proposed to make the simplest possible choice for this universal function of the Carnot theory. So if you take for f the identity function and you call it thermodynamic temperature, you directly have the modern definition of thermodynamic temperature, which is this equation here. The ratio of the heats are equal to the ratio of the thermodynamic temperature. According to measurement theory, thermodynamic temperature scale is a fourth type of measurement scale. It is called a rational scale, and it establishes equality, order, equal intervals, equal ratios, and it has a natural zero. Of course, in the case of temperature, the natural zero is the absolute zero. So temperature evolved in a similar way to other SI fundamental units. Initially, there was a kind of nominal scale. So initially there were nominal scales in the sense that we distinguished only between cold and warm, unconsciously, of course. Then different degrees of warmer and colder were introduced. So we introduced ordinal scales, and as I showed you before, the empirical temperature scales are ordinal scales. Later on, with the development of thermodynamics, interval scales were introduced. I just showed you the Thomson scale, and also the modern Fahrenheit and Celsius scale are interval scales. Sorry? Is there a problem? Hello?
No, just go on.
No, please go on. There's somebody having a microphone on, but I can't cut it. So.
Okay, sorry. So, and then further, with further developments of thermodynamics, we introduced the rational scale, which is the present thermodynamic temperature scale. So I speak about evolution in the sense that the more we learned about temperature and its true nature, the more the scale was able to encode the structure of temperature in the numbers we used to measure it. And this is formalized in the so-called representational measurement theory, according to which a measurement scale is a correspondence between the space of the quantity, the hotness, so temperature, and the space of the numbers we attribute to the quantity. So representational measurement theory says that a measurement scale assigns number to a quantity, but when we use numbers, we have to be careful because numbers can always be manipulated. You can always add, subtract, divide, multiply the numbers, but the relations, the operations that you can perform with the numbers do not always correspond to meaningful relations among the quantities measured by those numbers. According to representational measurement theory, numbers are adequate for expressing quantities only when the correspondence is one-to-one between the empirical space and the image space. So here I'm showing the table which summarizes the type of measurement scales according to the classification of Stevens, which is one of the fathers of measurement theory. You see again a nominal, ordinal, interval, and rational scales. And in the second column, you see the mathematical operations which you can perform among numbers. So the mathematical operations which are meaningful for each one of these scales. In the third column, you see the transformations which are allowed for each scale. So the transformations that leave the scale undistorted. I will make a couple of simple examples to explain this. If you take the modern Celsius scale, if we have 18 degrees in Paris and 9 degrees in Moscow, does it make sense to say that the temperature in Paris is twice that in Moscow? Of course, it does not make any sense because we are in an interval scale, and as you see in this table, for an interval scale, ratios do not have meaning. On the other hand, if we have 18 degrees in Paris, 9 degrees in Moscow, 32 in Bangkok, and 23 in Los Angeles, it does make sense to say that the temperature difference between Paris and Moscow is the same as the temperature difference between Bangkok and Los Angeles, because Bain and interval scales, equal intervals are meaningful. Another simple example about the scale transformations. Well, you all know that you can transform a degree Celsius into degree Fahrenheit by taking the degree Celsius and multiply it by 9, dividing by 5, and then adding 32. And of course, this is a scale transformation, and this is allowed because Celsius and Fahrenheit are interval scale. And if you look at the table, you see that the linear transformation is the only transformation which is allowed for interval scales. If we take a rational scale like the Kelvin thermodynamic scale, well, one could say, I don't like the triple point of water temperature to be at this very strange value, 273.16. I prefer the number 7. And one could change, of course, the thermodynamic temperature scale in a way that the triple point gets number 7 by simply applying a scale factor to all the temperatures. Of course, this is not probably a very good idea, but it is in principle possible, and the scale would have all the properties of the rational scales. Okay. Now I come to the second part of my presentation. It is just a few minutes more, just 5 minutes, so please bear with me. Before 1927, I hear some background noise, but okay, I will just go on. Before 1927, the unit of thermodynamic temperature was defined by fixing a temperature difference of 100 degrees Celsius between the ice point and the steam point. So in 1927, the thermodynamic Celsius scale attributed 0 degrees to the ice point and 100 degrees to the steam point. And the thermodynamic Kelvin scale was established based on a temperature difference of 100 Kelvin between the ice point and the steam point, without attributing numerical values to the ice point and the steam point. In the same year, the International Temperature Scale of 1927 attributed 0 degrees Celsius to the ice point and 100 degrees Celsius to the steam point. So we had 3 scales, and the units of the 3 scales were identical. Already in 1948, the CGPM, on the advice of the CCT, accepted the principle of a thermodynamic temperature scale having a single fixed point provided by the triple point of water. The problem at that time was which numerical value should be attributed to the triple point of water. Okay, so in 1948, the problem was which numerical value should be attributed to the triple point of water. But already in 1948, the interval between the ice point and the triple point was known accurately. It was 9.93 milledegrees Celsius. So it was already clear that in the thermodynamic Celsius scale, the triple point of water had to take the value of 0.01 degrees Celsius. The problem was which value should be attributed to the absolute zero in the thermodynamic Celsius scale, or equivalently, which value should be attributed to the ice point in the thermodynamic Kelvin scale. In 1948, the CCT was not ready yet to answer this question. The value was not known with sufficient accuracy. But the CCT was ready in 1954. During the CCT session of 1954, the 4 main laboratories which had worked in the past decades at the determination of the thermodynamic temperature of the ice point were asked to come up with their proposal. The 4 labs were PTB from Germany, Kamerlingh-Ohm's labs from the Netherlands, Tokyo Institute of Technology from Japan, and MIT from the US. And you see, 3 of the 4 labs came out proposing 273.15 to the thermodynamic temperature of the ice point, and MIT proposed 273.17. And during the meeting of 1954, the CCT decided for 273.15 for the thermodynamic temperature of the ice point. So in 1954, a new thermodynamic scale with a single fixed point at the triple point of water and with a numerical value of 273.16 Kelvin was introduced. And to preserve the continuity with the past scale, the ice point and the steam point were kept at 0 degrees and 100 degrees Celsius, but this time by convention and not by definition. In 1976, gas thermometry measurement at MBS showed that for this new scale, where you have one single fixed point at the triple point of water, the temperature of the steam point is not exactly 100 degrees Celsius. It is close to 99.974 degrees Celsius. So this showed that the size of the Kelvin in the new thermodynamic scale was different, was larger from the size of the Kelvin in the old thermodynamic scale. And also to maintain the ice point and the steam point at 0 Celsius and 100 Celsius in the thermodynamic Celsius scale, the absolute zero should have been minus 273.22 degrees Celsius. Okay, now we come finally to our days. In 2019, we had the redefinition of the Kelvin. So you see that in 2019, the triple point of water still has the value of 273.16 Kelvin, but this time it is not by definition. It has an uncertainty of 200 microkelvin. So the numerical value of the triple point could change in the future. For example, if in the future we have a primary measurements at the triple point of water, so an experiment similar to the Boltzmann experiments that we had in the past decade, well, it could redetermine the numerical value of the triple point with a lower uncertainty than 200 microkelvin. And in this case, the numerical value of the triple point of water could change. Okay, I think I'm close to the conclusion. I wanted only to show again my slide about the evolution of the temperature scale. And I wanted to conclude by, considering what has changed in this evolution with the redefinition of the Kelvin in 2019. Well, the type of scale has not changed. It is still a rational scale. The triple point of water from 2019 can change, but without affecting the size of the Kelvin, because the size of the Kelvin is not linked anymore to the triple point of water value. The size, the magnitude of the Kelvin has changed, but in a not perceptible way. It was only 2 microkelvin at the triple point of water and 9 microkelvin at the silver fixed point. Concerning the definition and the meaning of temperature, well, it is basically unchanged. There is, I would say now, more emphasis on the fact that temperature is the average thermal energy per degree of freedom in the system, and not only a thermodynamic temperature, but also a statistical thermodynamic temperature. And this is the end of my talk. I would like to thank Rod White for the very interesting Zoom discussions we had and our correspondence, and also Richard Raspi for our correspondence. Thank you for your attention.